So we are on our last section here of, apparently, of chapter 13, and we are still talking about single electrons. And why I say that is because I've seen their terminology, and this is what's coming up. So what they're talking about today, I think hopefully in about 45 minutes, you'll see the big picture. But right now, the author is going to be kind of jumping around from here to here and there, and just hang in there. But we spent a day of coupling, so I think it'll smooth things over a little bit. But I say a single electron still because I see little j's, little l's, and little s's. And what's going on here is there's motion. What type of motion are we interested in again? We're talking about orbitals, those sorts of things. Angular motion, right? It has to be this repetitive, this cycle motion. We're not talking about things flying translational motion. We're talking about this angular motion. So you've got the spin of the electron. So we're talking about its individual electron, right? It can be in all these different energy levels, and it's got this angular momentum. And it's got the angular momentum that's due to this orbit, right? It's got to stay in this, I kind of picture like this p orbital, right? Or an s orbital, a sphere. It's got this angular momentum that it has to have. It's a circular motion. But then they call it the intrinsic angular momentum, and it's spinning. So just by it existing on its own, it's got some angular momentum. So what they're trying to get at then is this kind of thing. See how they've got little s pointing up, and then they've got these bigger arrows with L's. And what they're trying to say is that, okay, you have these arrows again are supposed to represent what type of momentum? Angular momentum, right? So you kind of put your thumb of your right hand in the direction of the arrow, and you see the direction of the angular motion. Remember that? Okay. So where are these two angular momenta coming from? Again, one is from L, right, the orbital angular momentum, and one is from S, which would be spin angular momenta. Okay, and I like that at least they drew S a lot smaller because it should be smaller, right? And how do you get this angular momenta? We drew diagrams like this over here, but the point is why do you draw that S that long? What's the equation we're supposed to be using? How do we know the length, the magnitude of this angular momenta? What was our general equation?
J times J plus 1.
Times H bar. Hear what she said? So if we want to talk about spin, it'd be the square root of S times S plus 1. H bar. If you're talking about angular momenta, L plus 1. Whoop, square root H bar, right? So that's the magnitude of this angular momentum. And since it's a charge and it's moving, it acts like a little tiny, starts with an M, magnet. Acts like a little tiny magnet. So these two types of angular momenta, right? One is due to spin, the other one's due to what, Alyssa? One type of angular momenta in this electron is due to spin. The other one is due to, but starts with an O, orbital. So I kind of pictured it as two origins of angular momenta, right? You've got one that's the orbit, you got the other one that's the electron spinning, but this sort of thing, I'm trying to conceptualize it into my macroscopic world, and I bet it's nothing like it, right? Because you can't relate one with the other. It's really hard. But they're trying to come up with why experiments work, and this is just what they're observing. And this is how they're explaining the end results. So these two different types of angular momenta each give rise to acting like a little magnet. So these two types of orbital angular momenta, they can be working together or they can be working against one another, kind of like a magnet, right? These two magnets could be lined up, north-south, so then they're at a lower energy, or north-north, where they're kind of repelling each other. And that's what they're trying to say here, is that you have the low energy, Well, I think of the low energy, whether the picture is kind of doing it right or not. Low energy would be where right, north is lined up with south, south lined up with north. They're attracting, right? They're not repelling. These two type of angular momenta. And then the other orientation, there's only another one where they're lined up. Why is there just two? Because energy is quantized and it's just a weird world there. But if you have these two types of angular momenta, well, then you can have a total angular momentum, and that's the J. So they want to say that J, right, is the total angular momentum. So now if you're going to have an L, so this is what? L is 2. If L is 2, I'm really talking about what type hydrogenic orbital? If L is 2, a D. And I'm talking about just one electron, so something like this, D1, right? It could be 3D1, 4D1, whatever, but I'm talking about an electron configuration that looks like this. Again, just one electron. So little L is 2. S is, what can S be?
Either half or minus half.
Yeah, half or minus. They're always taking it would be a half, right? So S is a half, L is 2, right? L is 2, S is a half. And then you have to couple them. Well, how did we couple again? If we couple two things, it's the sum all the way down to their difference. Okay, so we've got 2 plus a half is 2.5, which is 5 halves. So L plus S all the way down to L minus S. So you'd have 5 halves all the way down to 3 halves. So and that's what our J is, right? Our J is, again, these are smaller case, following their notation, because they want just one electron. They use smaller case letters. So there's just two possibilities for J, and then we could draw these projections. So they drew how, again, the length of the arrow, you can get it from the square root of L times L plus 1 h bar, right? Or square root of S times S plus 1 h bar. So that's how they're drawing the lengths of those arrows. But you can couple them. You get two possibilities for J, 5 halves and 3 halves. Okay? And what they're trying to say, let's see here. Oh, let's follow this so we don't skip anything. Singlets and triplets. So if you have, it really falls into this, 2s plus 1. So what does S come out to be? If you have one electron, so your S is just going to be a half. A half times 2 is 1, plus 1 is 2. So that wouldn't be a singlet or a triplet. That would be a doublet. But what if you had 2 electrons? How do you get the S? You have to couple them. And we'll get that when we get down to more, right? But this is where they're coming from when they say singlets and triplets. If everything is paired up, S is 0, you just have a singlet. And this will make more sense when we get towards the end, I think. Okay, but so we have our energy levels now, are different. And I don't have the terminology. They use the word level. You're going to see the word level a lot. We like to say energy levels, but now they're just talking about level. When they use the word level, they're saying everything with the same J. That's just what their convention is. And again, like I kind of warned you, right? This stuff is going to be odd until we kind of get to the very end and we can kind of see the big picture. So just kind of hang in there. So you have everything with the same J they call the same level. Now, how do you get these energies? Pretty much you just plug in what, again, one electron, plug in what J, L, and S are, and you get now you get the actual energies, okay? And A is the spin-orbit coupling constant, so it's just going to be some number. H, Planck's constant, C, speed of light. But notice how would you get the lowest energy? Just by looking at the equation, you want J to be really, if you want the lowest energy, J to be really small, L to be really
Big.
big and S to be really big. So what we're going to, and that works, that logic works when a shell is less than half full. Right? Like 3p2 or something. And that's pretty much all of our homework is going to be that way. Okay. Otherwise, it's kind of weird. You want big J. But I don't think we're ever going to really see that, so we need to really worry about it. Okay. So this idea of the orbital angular momenta coupling with the spin angular momenta, they call that spin-orbit coupling. Okay, and that's where they're coming from. That again, this is all just for one electron. So there's our total angular momentum. They want to use the little symbol J for that, for one electron. So if you, is it possible to have 0 orbital angular momentum? Is that possible? The magnitude of the orbital angular momentum is 0. Is that possible even? Could this, in other words, can this equation ever equal 0? Yeah, sure. Why not? If L equals 0. Well, what orbital is that? S. So if you have these S orbitals, they're perfectly spherical, the net orbital angular momentum is 0. So if there's no orbital angular momentum, it's kind of a trick question. Then you can't have any spin-orbit coupling because there's no orbital angular momentum. Okay. But I don't know if that's really helped. You mentioned level. That just means the same J. The same J value. Okay. So if you have, where this is coming from is before, well, since you have L and S now, if they're not 0, you have spin-orbit coupling, and then you're going to, not everything just depends on J anymore. That you have this level J, but if you apply a really strong magnetic field, you can actually see splitting. And that's due to spin-orbit coupling. Okay, and that's what they're trying to get at here. That's what's messing with NMR. But let's see if you believe it. If I have this electron configuration, again, we're just talking about one electron. So I'm not 2p1. Okay? So where are they getting this stuff from? Well, first, where did they get these two from? They coupled what to get 3 halves and 1 half? They coupled little s and L. They coupled those two, and then they got 2 possibilities for J. So little s's, they used probably what? A half. Glorianne, they probably used what for little L? Since we're talking about this. 2p1. What's little L have to be?
1.
Remember? Let's review that. L could go 0, 1, 2, 3, on up, right? What were the orbitals again? If L is 0, you have a what type? S. P.
F.
Yeah, and then it gets alphabetical, right? So that's where they coupled L is 1 and S is a half. Couple them, they're summed down to their difference, and you get those two, right? You agreeing so far? Now where are they getting this stuff? the actual joules. Right here. So if you actually plug it in, what is it? I lost it already. 1/2 HCA. Let's try it. 1/2 HCA times what? J times J plus 1. J times J plus 1. Minus L times L plus 1. Minus, whoop, L is 1 times L plus 1. Minus S times S plus 1. Minus 1/2. I'm running out of space here. Times 1/2 plus 1. Okay, so you'd end up with, what, you'd have a 1/2 HCA. Hopefully this is going to work. Let's see. 3/2 plus 1, that's 2/2, plus 3/2 is 5/2, times 3/2 should be 15/4. I'm doing stuff in my head, and that's dangerous. Does that sound right? Mm-hmm. Okay. Minus, let's put it in terms of force. We've got, so it's minus 2. Well, in terms of force, that would be minus 8 force. So hopefully we're not losing you. All right? Jeffrey, you see why we wrote 8 force?
Yeah.
Okay. Now it's, well, I can't even read my own writing. Was that 1/2 plus 1? That's 3/2 times a negative 1/2 is a negative 3 force, right? Right. 2 3/2. Right? That should be right. 15 minus 8 is 7, minus 3 is 4. 4 over 4 is 1, so you end up with a 1/2, yeah, 1/2 HCA. A lot of work to get that, but that's, it works. So how'd they get the bottom one then? Same way. Just use a different J. Right? So that can be a you do. Okay. So they're trying to say the level is everything that has the same J. The number of states, when they talk about that, that's the number of different types of J values. And again, this is going to be, I think this is going to make a lot more sense at the end when we start actually writing term symbols. Okay, so just trying to get some terminology in here and seeing where this stuff is coming from. This is what we're really just trying to do now. I think I've mentioned everything. Okay. Now, what's important here is to realize the transition. See the little small L's, small S's, small J's? Section 13.9 jumps in. Not small L anymore, big L's, right? Not small s, big S. Not small j, big J, okay? And that means we have many electrons, multiple electrons, right? So now that we have big L, big S, big J. Here's how we get them, right? Couple. There's some down to their difference. Couple all the L's. Right? If you have just 2, couple them. Get all their possibilities. Couple the S's. Couple your resulting L and S's, and you get the J's. Okay? So that's kind of where they're coming from here. So we're starting to write term symbols now. So this is the convention. So for each state, we'll be writing a term symbol. Then by looking at the term symbols, we can talk about transitions and that sort of thing. So and out of this term symbol, we can calculate energies. So if the L value is 0, you're supposed to write the symbol capital S. Well, if capital L is coupled to your orbital angular momentum, your total orbital angular momentum, it's capital L. If it's 0, it's the symbol's S. What do you think it's going to be for 1? Yeah, right? They're just following. 2 would be D. All right, see the game they're playing? 3 would be F. Okay, so they're just following the same convention they used for hydrogenic orbitals. Okay. Multiplicity. Okay, well, you've got 2 electrons. Let's say S1 is a half, S2 is a half. So written this way, are these electrons paired? No. Because if they were paired, you'd have one being a half, the other one being negative a half. So these are 2 unpaired electrons. What would be our total spin quantum number, S? It's going to go from what to what? 1 to 0. You have to couple them. So is there anything in between? No. So then this idea of multiplicity, remember that talk of singlet, doublet, triplet, that idea? You put them in here, right? So you put your total spin quantum number S in, 0, you would get a multiplicity of 1. So we would call that what, Alyssa? Call it a, if your multiplicity is 1, you're supposed to call it a singlet. You know, with 2, doublet, 3, triplet, right? So here's just the names. I mean, the total orbital angular momentum quantum number, total spin quantum number, total angular momentum quantum number. So here we're coupling. Can you see what the hydrogenic orbital would be? Little l is 2. So that would mean we're really talking about a D, right? What is that? And then this guy. See here, little l is 2, little l is 1. So kind of like this. So where's this stuff coming from? They're really talking about, okay, we're going to one is a P. So they're talking about these guys. Let's couple them. Couple their orbital angular momentum. See what the end result is. That's why I have L is 2 and L is 1. Couple them. They sum down to their difference. So you get 3, 2, and 1. Right? So that's all they're really just doing. They're just coupling. And it'd be easier to see, I think, when they ask a homework question, but these are the tools of the trade that they're using. I already mentioned multiplicity, 2s plus 1. Page 379. I didn't skim it, did I? I don't know if this even matters. I don't even have it in your notes. What's on page 379? Let's check. I was looking at a correlation diagram, and I scribbled down page 379. I don't know what I'm trying to... I don't think there's anything there, but... Oh, it's a funky plot that looks like this. There's trying to say there's different ways of, there's different rules for coupling. That's why that JJ coupling is there. We're going to couple with, we spent a day doing Russell-Saunders coupling. That's a technical jargon of what we did yesterday. So that's what we're going to be doing. We're going to be following Russell-Saunders rules of coupling angular momenta. Okay, and there's different ways of coupling depending on the situation. So if you have heavier atoms, the way we're doing it may not be the smartest way to go. But so these are the rules we're following. Okay. Well, we've already practiced that. Much to mention here. I guess what they're saying here is you're not going to see all this work we're going through of coupling and spin orbit coupling and seeing all these different possible states. You're only going to see it in the presence of a really strong magnetic field. Otherwise, you don't get all this splitting. Okay, but that's the whole idea of what type of spectroscopy. So you can get this splitting and actually get some spectroscopy going. So there's an N, then an M, NMR, right? So instrumental, we just talked about that. But I don't think we're going to mention that here. Okay. So let's see what this homework looks like. If we fly through this, then this is all just one day, but I don't have any notes about this. Let's see what it looks like. Let's start with the A exercise 8 through 16 and see what this does. Calculate the permitted values of J for a D electron. So I don't think these are that bad. Let's check them out. We have a D electron. They want to know what J is. Well, the only way to know what J is if you know what and what are. S and L. Okay, so you've got a D electron. So that means L must be 2, S must be a half. Right? So couple them, and you'll get the permitted J values. Right? An F electron. How does that work? I got to number this out. I'm going to screw it up. So if you're an F electron, it's 3, right? Here L is 3. And Gloriana, S would be a... let's see. Let's back up. D electron. How many orbitals? 1, 2, 3, 4, 5. And just one electron. Because they say A electron. Okay, so to describe this system, right? L is 2 because it's D. S is 1/2. So we couple these two, sum down to their difference, and you get the possible J values. Do the same thing here. So here, my question to you was, okay, F electron. So I had to count these out. Oh, I screwed up every time. Right, so L is 3. S would be?
S would be...
Before it was a couple 2.5. Now I'm just going to couple. Right.
What would be 6?
There's 7 orbitals in there. S, anyone help her? S has to be half, right? Just an electron, right? Just, we think of going down as minus a half, I guess, but the math is always easier with the one going up. So we're talking about electrons, so little s can always, what are its possible answers? For an electron, little s. Oh, 1/2. Half or minus a half, right? It's a lot easier to pick a half all the time. Okay. Little l, well, depends on the hydrogenic orbital, right? So you can finish that. Right? You comfortable with 8, I think? Melissa, you see what to do? How about in 9? An electron in two different states of an atom is known to have J as at 3/2 and 1/2. What is this orbital angular momentum quantum number in each case? What symbol are they looking for?
L.
Looking for L. Okay. Well, that's not so bad, right? See how to do 9? Alyssa, you see what to do there for 9? Okay. What's that? Yeah, you work backwards. 'Cause, J has to be L plus S down to L minus S. And S has to be 1/2. They're just talking about 1 electron. So you can figure out, you have to deduce what L would be then. Yeah, it just has to be 1. And 11. What information does the term symbol provide about the angular momentum of the atom? So what are they asking for now? That's different than what they said in 9.
The L value?
Yeah, but that's not the complete answer.
L equals 2.
They want the angular momentum. How do you turn these quantum numbers into momentum?
All of that.
How do we do that?
Square root of L.
Times L plus 1 times h bar. So what you got to do is figure out what L is and then substitute into our expression.
What does that D2 mean?
Oh, the little 2,
It's just 2.
right? That's the value of the J. That's the J value. And remember, what they're talking about is everything that has the same J value is on the same level. That's just, right? It may not have the same energy, but it has the same level. Okay, pretty much because the total orbital, the total angular momentum is all the same. Okay, so how are you going to, so we're going to see how to do 11? What would be the answer? You could say that L is 2, right? Is that what we're saying? And you could say the orbital angular momentum would be right? That's how long you draw the arrow. It's pretty much all you can tell. It's all the information we can give. Suppose that an atom has, so stop me, man, if I'm just moving along here too fast. Suppose an atom has 2 electrons in different orbitals. Okay? Draw a bunch of orbitals here. And there's 2 electrons in different orbitals. What are the possible values of the total spin quantum number? So how would you start this out? Now, first, when they talk about the total spin quantum number, what symbol are they referring to? Small s or big S?
Big S.
Big S, because it's total. That's the only thing I can think of. You just have to get used to this. It's not that hard once you get used to it. So that's big S. And how do you get big S? You
The sum over to the difference?
exactly. You couple the little s's. So you couple the little s's to get the big s's. So what little s's are you going to couple? A half and a half. You couple a half and a half, and you'll get the big s's. Part B, you would couple what to get the big s's? What would you couple? Half, half, half. Right? So couple the first 2, get your results, call it an S prime or something, and then couple those with a half again, you'll have your answers. Again, we did that, I think. Yeah, we did some examples of that last class period. Okay, you're comfortable with 16? See what to do? In 8, calculate the permitted values of J for a p electron. Now again, that's small j. So how do you get small j? Of what?
L.
Little l and little s. So you have to figure out, they should have told you enough information to get what little l and little s are. So, and you couple them. Little l, I'm just putting ones on there because it's just nice to be consistent. Little l and little s. And plus then you can tell it's little l and little s if I put little subscripts. If it's a p electron, little l has to be what, Gloriana? Has to be 1. Then everybody, little s has to be?
0.
It's a p electron though. If it was an s orbital, s has to be a half. Right? A couple of those, you get the permitted j values. H electron, do this exact same thing. I wonder if 9 wants me to draw pictures. No. There's not much of a hint. We already know this. If you know what little j's are, couple them to get the big j's, because that's the total angular momentum quantum number. So I don't know what this hint, you don't even really need it. How do we do it again? Their sum down to their difference. So that's how you get big J. Again, here, this is really similar to 11A. All right, we already answered one of those. Calculate the magnetic induction B in 20. Calculate the magnetic induction B required to produce a splitting. We better go back and look at the notes here. There's an expression to do something here. Oh, I bet I didn't write it down. Was I supposed to have written it down? I was supposed to have written it down. Okay. So this Bohr Magneton is just a constant. Look at the inside front cover. So look and see what it is. I can just tell you what it is. Might be faster to Google it. Oh, there it is. 9.27 times 10 negative 24. Units are joules per T. Now, what's T? It's a unit. So it's not a variable. It's not T for temperature. Tesla. Someone remembers their magnetic stuff, right? So that's joules per Tesla. So when you solve for B, right, B, the magnetic strength, you get your answer in Teslas. So you got to watch your units here. So you know what the Bohr Magneton is, but remember it's in joules per Tesla. We'll solve for B, we'll get Teslas. That's good. The trick is this part right here. They said a splitting of so many wave numbers, right? So how do you get wave numbers into a delta E expression?
Oh, HC or lambda.
Yeah, let's start from the beginning. So you remember this. So you remember this. You're exactly right, Melissa. H nu. HC over lambda. Keep going. HC.
1 over. Oh.
And, well, 1 over lambda. You're right. It's easier to remember the 1 over lambda than this tilde thing.
Yeah.
But this is what we did in our concept preview. We called that the wave number. But yeah, I could pretty much stop right here. Right? So there it is. But I think this is kind of nice right here because this fits the homework question really well. here's our wave number in inverse centimeters. That makes, so you can fix this just by putting C in what units. Because this is inverse centimeters, our wave number symbol. Put speed of light in centimeters per second, and everything is going to work out great. Because H is in, then just leave H alone in its units. And then everything works out great. Okay, so that's how I would handle that 20B. Okay. Again, what units should you end up with? Teslas. You should end up with Teslas. Okay. Okay. Make sure we're on the right track here. So I think we're ready to go on to these problems. Characteristic emission. Yeah, I was following the order here. I thought there's a reason. Did I skip the handout?
Yeah.
Oh, I skipped the handout. Shoot, I want to follow this order. There's a reason for doing this. Because we're not ready to do, that's what I was thinking. I was reading this, and you guys haven't even talked about this yet. Okay, so we haven't done a problem like that, so that would be really tough. Let's follow this order of doing things. So we just talked about 20, right?
Mm-hmm.
Okay, so now we should do this handout. Okay, now we should talk about that handout. So handout 13A. Where's handout 13A? Here it is. This will make things much easier. So let's go ahead and start this 13A. So if we do this 13A, look at that. Wow.
So we should stop at the line.
Yeah. Stop at the line and save that for next time.
Yeah, but then we already did all this homework for you.
We got 4 more minutes.
Okay, so where are we then?
Stop at this line.
That's probably why we did.
Remember, there's a line there for a reason, Dr.
Yeah. Alrighty, fine.
What do you say? Alrighty, fine.
Now just realize though, by stopping at the line, this is going to be a lot. But we have to stop. You're right. We're out of time anyway. So now we'll stop at the line. That's probably why it's there. That's not going to be a lot. Now I'm going to make you think bad. This is easy. Alrighty. So have a good day.